Hey folks, this is Kevin Jones here to talk to you about interrupts, the second part, which is once the processor has been signaled, how does it actually handle this interrupt request? So, kind of what happens on, you could almost imagine kind of on the software side. So our objectives are to describe the sequence of events that occur when an interrupt service routine is requested. Along part of that process involves an area of the memory map called the interrupt vector table. So you'll know what that is by the end of this lesson. And since the interrupt service routines are very similar to the OS service routines, we're going to do a little comparison of those two, specifically kind of how they're able to get the correct starting address, since everything else is very similar. So let's get started. Okay, so this is a picture of the memory map for the LC3, and hopefully this looks very similar to what we saw in a previous lesson on operating system routines. What we're going to imagine is down here in user space, I'm executing some code, and then right in between the load and the add instructions, the interrupt occurs. Or like we know from the previous lesson, the interrupt may occur during the processing of the load instruction. And it's as soon as that instruction finishes and the LC3 goes back to the top of the instruction cycle that it sort of sees that there's an interrupt and is able to respond to that. So the interrupt service routines live in system space, just like the operating system service routines. So if we're down here, we have to execute the same first few steps in order, as we did for the operating system routines, in order to get from user space to system space. So first thing we do is we save the user stack pointer to a special register in the processor. We load R6, our stack pointer, with the supervisor stack pointer, since we're moving to the system space. We're going to push the processor status register and the program counter onto the supervisor stack. So that's how we sort of save the state of the processor prior to going to our interrupt service routine. And then lastly, we're going to clear bit 15 in the processor status register. Recall that that's going to move us from an unprivileged to a privileged mode. So step number 2 is to get the value at the vector address, whatever vector is being pointed to by that interrupt. We'll talk about that in a sec. And then branch to that value. So in this example here, we're going to assume that the vector that's generated by the keyboard interrupt points to address 0100, and at that location is just address A. Address A in system space here is the keyboard ISR. Okay, so it's very, very similar process to how the operating system service routines are initiated, where we have a vector table in the lower system space here that has addresses for the starting instruction for these service routines. So just like the trap vector table was located here from address 0 to 0FF, right above that we have something called the interrupt vector table that starts at 0100 and goes up to 01FF. That contains the starting addresses for my interrupt service routines. Actually, I'm feeling like I'm probably going to update my notes. This should probably be here. We'll look at later. In actuality, the way the book describes it, 0180 is the vector for the keyboard interrupt service routine. So I think I got this in the incorrect row. Yeah, because even my arrows are pointing to this row right here. So, we'll assume the keyboard interrupt service routine is what occurred. It's going to look at memory address 0180. It'll find, in this case, just some address that'll take the processor to the keyboard interrupt service routine. And then just like our operating system service routines, these will end with the RTI instruction. The RTI has to take us back into user space, so it performs sort of like step 1 in reverse order, which are to pop the program counter off of the supervisor stack into the program counter register, pop the processor status register off of the supervisor stack, and reload that. So now we've effectively restored the state of the processor. We will save the supervisor stack pointer wherever that's at in a special register in the processor. And R6, the stack pointer, will get reloaded with the saved value from the user stack pointer that we saved here in step 1. And then the last thing is going to be to set the privilege bit in the processor status register to indicate that we're moving back into user mode. I don't think I have that note here, and I'm realizing now I think I might have forgotten it in the other lesson on the system routines as well. So that's the last thing that the RTI instruction does. And then just like our operating system service routines, once we complete that instruction, our processor starts executing this add instruction as if the interrupt had never occurred, meaning that between the load and the add instructions, the state of the processor is exactly the same minus whatever this keyboard interrupt service routine did. So just like our operating system service routines, it's possible for interrupts to occur within interrupts, or for an interrupt to occur in the middle of a trap service routine. The process is a little bit simpler than we just looked at, for the same reason that it was simpler for the trap service routines, which are if we're already in system space, then there's less that we need to do in going to and from an interrupt service routine, since we're already in sort of privilege mode. So we'll assume in this scenario that we're executing some operating system or interrupt service routine and an interrupt occurs. In that case, step one is going to be to push the processor status register onto the supervisor stack, push the program counter to the supervisor stack, and then get the value that we need, or the starting address of our interrupt service routine from the interrupt vector table. We'll branch to that address. In this case, we'll assume it's the keyboard interrupt service routine that's been triggered. So we run the keyboard ISR. That ends with the RTI instruction, which performs step one in reverse. So we pop the program counter into the program counter register. We pop the processor status register back into the processor, and then we start executing code in this service routine right where we left off. Okay. So the steps for both an operating system service routine and an interrupt are very similar. They're almost identical, except for this step in the middle where I'm getting the address of my service routine and branching there. The process of doing that is slightly different for these two service routines. So if I'm executing a trap instruction, then it is the vector that I'm looking at for my starting address is embedded in this instruction. So recall that in the trap instruction, the lower 8 bits specify this vector, and so if I execute trap 21, that means I'm trying to find the starting address of my operating system service routine at memory location 0021, 00. These two values are prefixed to the vector, which indicate that we're looking effectively in the trap vector table. So the trap vector table occupied these first 256 locations in memory. So we prefix 00 with whatever vector is in the trap instruction. That's where we find the starting address of our operating system service routine. For interrupts, it's slightly different. We are going to find the address of our ISR by using the prefix 01. So this is going to be our interrupt vector table. Recall that the interrupt vectors occupy these 256 spaces in memory that all go 0100 to 01FF. So 01 is the prefix that indicates we're looking at our interrupt vector table. And then we get the interrupt vector at this point basically somewhere that's hard-coded into the processor. So the details are a little sparse on this in the textbook. But if you jump to Appendix A, there's a discussion here on interrupts, A.3.1, which mentions that basically the keyboard interrupts has a vectors x80, hex 80. And so, so what this means is that the best way that I can think of it right now is that even though there are spaces for 256 interrupts, the simplest way to think of this is that based on the hardware we saw in our previous lesson, we are able to support a total of 7 interrupts. And the reason is because we need something of a unique identifier when we trigger this interrupt to figure out which interrupt is being serviced. And the logic, the circuitry gets a little complicated if we are trying to support many interrupts. So we'll make the simplifying assumption that even though our interrupt vector table has 256 spaces, and maybe technically our processor should be able to support 256 different interrupts, we'll assume right now that it only supports 7. So this encoder, this is the same encoder from this lesson on the hardware right here, where all of our different interrupt requests are sort of plugged in, and it's going to output the highest priority interrupt that is requesting service. So the keyboard interrupt, like the text says right here, is hard-coded to a priority level 4. So the encoder will output the highest priority interrupt that needs servicing, and then we'll assume there's a little piece of memory here, that's eight spots tall that holds the interrupt vectors for each of these interrupt requests. And so we'll assume here that memory address of 4, which corresponds to the keyboard interrupt, has the value 80. And so then if the keyboard interrupt is the thing being serviced, this value here going into the memory will be 4. The memory will output the value 80. When that gets prefixed with 01, we get our keyboard interrupt has a starting address located in memory 0180. And so you can see that here, 0180 holds the starting address of our keyboard interrupt routine. Okay, so the last thing I want to talk about is that there are potentially multiple different interrupt sources that could go to our processor, not just keyboards and potentially displays. Processors, lots of microcontrollers have timers on board that can sort of count clock cycles and alert the processor or interrupt the processor when certain timers have expired or are rolling over. Brownout is a condition where the voltage to a processor gets low enough that the circuitry might not work correctly. So lots of processors will have brownout detectors, and when they sort of detect that the supply voltage to that processor is dropping too low, they can interrupt the processor to kind of let it know that, hey, there's something that might not be right, and let the processor sort of try to pause anything it's doing, so that it doesn't try to do stuff that's erroneous. We'll look at later that there are a number of other things that we might connect to our processor, a number of other hardware devices that are very useful. Analog to digital converters is one example, and so there's lots of interrupts we might want to get from our analog to digital converters if analog values are above or below certain thresholds, or to alert us, if when a conversion has completed. Additionally, there's lots of different errors that we might want to be made aware of, such like we might want to have an interrupt if we were writing to the display data register when it wasn't ready, or if the keyboard data register was being written when it might get overwritten. So these are all different types of interrupt sources. On modern processors, there's support for dozens, sometimes even hundreds of different interrupt sources that all carry useful pieces of information to the processor and allow us on those modern processors to write programs that behave very responsively to things like these, events like these that might require very immediate attention. Okay, so today we finished out our discussion of interrupts by asking ourselves, okay, after the interrupt signal has been generated and our processor sort of starts this sequence to process the interrupt, what exactly is happening? And things were made a bit more simply by the fact that the processing of our interrupts behaves almost identically to how we already saw the processor handling the trap instruction. And so what that means is that there are, just like before, kind of 3 steps. We need to, at a minimum, sort of save the state of the processor. That involves pushing the processor status register and the program counter onto the supervisor stack. If we're in user mode, then we have to do a little bit of extra work here to save the user stack pointer and load the supervisor stack pointer and put us into our privilege mode. Then we look up the starting address of our interrupt service routine from the interrupt vector table and branch to that address. Once we finish executing our service routine, then we'll encounter the RTI instruction, which will restore the state of the processor by popping the program counter and the processor status register back into their places. And if we were originally in a user program and that interrupt occurred, then we'll sort of also restore the user stack pointer, and we'll also set this bit to put us back into an unprivileged mode. These two processes are almost identical, really, except for this one step where we're sort of getting the address and branching there. So we talked a little bit about how we get the address of the operating system service routine for the trap instruction from inside the actual instruction itself. And for an interrupt, that address is, at this point, it's kind of hard-coded in memory. Our keyboard has a priority level 4 according to the textbook, and so we'll use a little piece of memory here so that at memory space 4, we store the value 80 to create the spot in memory we need to look for the keyboard interrupt service routine. And then lastly, we talked about how there are a couple other, or in fact, lots of other interrupt sources we might want our processor to have, and in microcontrollers that we'll look at later on in the class, we'll see a number of these interrupt sources potentially, which are very useful to you if you're writing software for these devices. All right, folks, that's all I got. I'll see you next time.